Dear learners, I am Gaurav Kumar Agrawal, Assistant Professor working at UTD CSVT Bhilai. In today's session, we are advancing to the topic of foundation, that is shallow foundation part 2. We will explore the different types of shallow foundations such as strap footings, raft footings, machine foundations and discuss their applications. By the end of this session, you will gain a deeper understanding of shallow foundations and be prepared to apply this knowledge to the real world construction projects, ensuring stability and safety. We will discuss the following key points: first, strap footing; second, raft foundation; third, foundations for black cotton soil; fourth, footings at different levels; fifth, machine foundations. So, what is strap footing? A strap footing, also known as cantilever footing, is a specialized type of foundation used in civil engineering when a column is placed near a property boundary. This advanced foundation system consists of multiple individual footings connected by a structural beam called as a strap. The primary function of the strap beam is to distribute the loads from the column evenly across the soil beneath the footings without exerting pressures on the soil itself. Consider a situation where a column is situated close to the edge of a property boundary. If a traditional square or rectangular footing is placed directly beneath the column, it might extend into the neighboring property. This extension could be legally impermissible or physically impractical due to property line restrictions. In such cases, using a strap footing become a ideal solution. Then we are talking about the design and functionality of a strap footing. When the distance between two adjacent columns is significant, constructing a single large footing to cover both the columns, also known as combined footing, could result in an impractical, narrow or long shape, which might lead to high bending moments and structural inefficiencies. These inefficiencies arise because the footing would have to be designed to handle uneven pressure distributions and excessive bending stresses. To address this issue, a strap footing is employed. The strap beam in this system serves as a connecting bridge between two or more individual footings. However, unlike regular footings, the strap footing or beam is not in direct contact with the ground. It acts purely as a structural element, transferring the load from the column to the footing while keeping the pressure distributions under control. The strap beam is assumed to be perfectly rigid, meaning it does not bend or deform under the applied loads. This rigidity allows it to effectively transfer the loads from the more heavily loaded outer column to the inner column and then down to the respective footings. By doing so, the footing or the system ensures that the pressure distribution beneath each footing remains uniform and consistent, which is crucial for maintaining the stability of the entire foundation. Then the critical design considerations. First is alignment of loads and footings. The arrangement of footings in an strap footing system is critical. The center of gravity of the combined loads from the columns must align precisely with the combined center of gravity of the footing areas. This alignment ensures that the pressure distribution under each footing remains consistent, thereby preventing differential settlement which could lead to structural damage over time. Then the load transfer mechanism. The strap beam transfer the load from a heavily loaded outer column to the inner column. As a result, the strap beam experiences bending moments and shear forces. The magnitude of these forces depends on the distance between the columns, the loads applied to the columns and the relative stiffness of the strap beam and the footings. The design of the strap beam must account for these forces, ensuring that it can safely withstand the bending and shear stresses without the failure. Then the next is soil conditions. The effectiveness of a strap footing system is highly dependent on the underlying soil conditions. The soil's bearing capacity and compressibility must be carefully evaluated to determine the appropriate size and reinforcement of the footings and strap beam. If the soil has a low bearing capacity, additionally measures such as using grillage strap footings may be necessary to ensure stability. Then the material selections. Strap footings are typically constructed using reinforced cement concrete, also known as RCC, which provides the necessary strength and durability to handle the loads. In some cases, particularly where steel columns or stanchions are used, the strap beam and the footings may be constructed using steel, such as in grillage strap footings. This type of footing is particularly useful when a shallow depth is required. The soil has a low bearing capacity. Then the next step is construction process. The construction of a strap footing system involves several processes. First is excavation. Excavation is carried out for the individual footings at the specified locations. The depth and size of each footings are determined based on the load calculations and soil conditions. Then the next step is formwork and reinforcement. Formwork is erected to shape the footings and the strap beam. Reinforcement bars are placed within the formwork according to the design specifications. The reinforcement is critical for ensuring that the footings and the strap beam can handle the tensile and compressive forces applied to them. Then the next step is concrete pouring. Once the reinforcement is in place, concrete is poured into the formwork. The concrete must be properly mixed and compacted to eliminate air voids and ensure uniform strength throughout the structure. Then the next step is curing. After pouring, the concrete is allowed to cure for a specified period. Curing is essential for achieving the desired strength and durability of the concrete. The curing time may vary depending on the environmental conditions and the type of concrete used. Then the next is advantages and its application. Property line considerations. Strap footings are particularly advantageous in scenarios where property boundaries restrict the use of conventional footings. By using a strap beam to connect individual footings, the foundation can be kept entirely within the property boundaries while still providing adequate support for the structure. Uniform load distribution. The strap beam's ability to transfer loads between columns ensures that the pressure distribution under each footing is uniform. This uniformity reduces the risk of differential settlement, which can cause structural issues over time. Then the next is flexibility in design. Strap footings offer flexibility in design, allowing engineers to tailor the foundation system to the specific needs of the project. Whether dealing with varying soil conditions, different column loads or unique site constraints, the strap footing systems can be adapted to provide a stable and reliable foundations. Then the next type of foundation is raft foundation. A raft foundation, also known as a mat foundation, is a large continuous footing that extends over the entire footprint of a building, supporting all its columns and walls. This type of foundation is particularly useful when dealing with soils that have low bearing capacity, or when the structure imposes heavy loads that would make individual spread footings uneconomical or ineffective. Then what are its various key features and advantages? First is uniform load distribution. A raft foundation distributes the building load evenly across a large area. This uniform distribution reduces the stress on the soil beneath, making it an ideal solution in conditions where the soil has a low bearing capacity. By spreading the load over a wide area, the risk of excessive settlement or soil failure is minimized. Then the next feature is mitigation of the differential settlement. One of the primary reasons for choosing a raft foundation is its ability to mitigate differential settlement. This is especially crucial when the underlying soil consists of compressible layers or exhibit varying properties across the site. Then the next is economic efficiency. In scenarios where building loads are significant or soil conditions are poor, using individual spread footings for each column could lead to large, deep and expensive footings. A raft foundation by construct can be more economical because it covers the entire building area, reducing the need for deep excavations and extensive reinforcement in multiple isolated footings. Then the design variations. First is flat slab raft. The simplest form of a raft foundation is a flat slab of uniform thickness that extends over the building's entire footprint. This design is most suitable for structures with moderate column loads and relatively small spacing between columns. The uniform thickness helps in maintaining simplicity in construction and ensures a consistent distribution of the loads. Then the next is thickened slab under columns. When the column loads are heavy or the spacing between the column is large, a flat slab may not be sufficient. In such cases, the raft can be thickened under the columns to provide additional strength and reduce the risk of punching shear failure. These thickened areas, also known as drop panels, helps to distribute the loads more effectively and prevent localized overloading. Then the next is two-way grid or cellular raft. For structures with very heavy loads, a more complex design may be required. A two-way grid or cellular raft foundation consists of a network of beams that intersect in both the directions, forming a grid pattern. These beams are typically deeper than the slab itself and provide enhanced support by creating a series of interlocked cells that distribute the load more effectively across the entire raft. Then the next is raft foundation with basement walls. In buildings with basements, the walls of the basement can be integrated into the raft design. These walls act as deep beams or ribs that provide additional structural support to the raft. This approach not only enhances the load bearing capacity of the foundation, but also ties the superstructure and the substructure together more effectively. Then the next is raft foundation on piles. In certain situations, the soil beneath the raft may still be inadequate to support the structure even with a raft foundation. In such the cases, the raft can be combined with piles. The piles are driven deep into the ground to reach a more stable stratum, and the raft is then constructed on top of these piles. This hybrid solution combines the benefits of both the raft and the pile foundations providing stability and load distribution across problematic soils. Then the next is load distribution and pressure considerations. In designing a raft foundation, the load distribution across the slab is a crucial factor. Ideally, the center of gravity of the loads from the building should coincide with the centroid of the raft. When this alignment is achieved, the upward pressure exerted by the soil on the raft will be uniform, balancing the downward load from the structure. Then the next is uniform pressure assumption. If the center of gravity of the loads aligns with the centroid of the raft, the design can assume a uniform pressure distribution. This simplifies the analysis and design process because the pressure beneath the raft is considered uniform, equal to the total downward load divided by the area of the raft. This assumption, however, is only valid if the soil conditions are uniform and the load distribution is relatively even. Then the next is ignoring the raft's self weight. The weight of the raft itself is typically not considered in the structural design calculations because it is directly supported by the subsoil. The focus of the design is on ensuring that the soil can support the loads imposed by the building above, not the self weight of the foundation. Then the next is reinforcement and durability. Raft foundations often require substantial reinforcement to maintain their structural integrity, especially when differential settlement is a concern. The reinforcement is designed to resist both the bending moments induced by the loads from the superstructure, the stresses caused by any potential settlement of the foundation. Then the next is heavy reinforcement. Given the potential for differential settlement, raft foundations are often reinforced more heavily than would be required by a simple analysis. This extra reinforcement helps to ensure that the raft can accommodate any uneven settlement without cracking or failing. Then the next is durability considerations. The design of the raft must also take into account the durability requirements, particularly in environments where the soil may be aggressive or where groundwater conditions could affect the concrete. Proper material selection, waterproofing and detailing are essential to prolong the life of the foundation. Then the next is foundations for black cotton soils. Black cotton soils, classified as expensive soils, present unique challenges for foundation design due to their significant shrink swell behavior. These soils contain a high percentage of montmorillonite, a clay mineral that causes the soil to expand when it absorbs moisture and contract when it loses moisture. This cyclic swelling and shrinkage can exert considerable forces on foundations, leading to structural damage. Therefore, designing foundations for structures on black cotton soils requires special considerations and techniques to mitigate these effects. Then what are the various properties of black cotton soil? First is swelling and shrinkage. Black cotton soils undergo substantial volume changes with moisture fluctuations. During the rainy season, these soils absorb water and swell, increasing in volume. Conversely, during dry period, they lose moisture, shrink and develop cracks. These movements can exert lateral and upward forces on foundations, leading to structural issues like cracking, tilting and even complete foundation failure. The next is cracking. The shrinkage during dry periods lead to the formation of wide cracks on the ground surface, which can extend deep into the soil. These cracks pose a risk as they allow water to penetrate deeper into the soil during the rainy season. Given these challenges, the following considerations are crucial in the design and construction of foundations on black cotton soils. First is bearing capacity assessment. The bearing capacity of black cotton soils is typically low due to their expensive nature. Accurate determination of the safe bearing capacity is essential, considering the long term effects of the loading and soil movements. Expensive soils often exhibit slow consolidation under sustained loads. As a result, the bearing capacity may decrease over time, leading to the settlement issues. In the absence of a detailed geotechnical testings, the safe bearing capacity of the black cotton soil is generally limited to 50 to 100 kilonewton per meter square to account for these long term effects. Then the next is depth of foundation. Foundations should be placed at least 50 centimeter below the depth where moisture movement occurs. This is to ensure that the foundation remains unaffected by the swelling and shrinking of the soil above this depth. Additionally, the foundation depth should be greater than the depth of any tension cracks that may form in the soil to prevent the foundation from being compromised. Then the next is removal of expensive soil layer. If the layer of black cotton soil is shallow, typically between 1 to 1.5 meter deep, it is advisable to remove it entirely. The foundation can then be laid on the more stable, non-expensive soil below. This method eliminates the risk posed by the expensive nature of the soil and provides a stable base for the foundation. Then the next is isolation from the expensive soil. When dealing with deeper layers of black cotton soil, complete removal is often impractical. In such cases, isolating the foundation from the expensive soil is crucial. This can be achieved by excavating a wider and deeper trench around the footing and filling it with a layer of non-expensive material such as sand or murum. This layer acts as a cushion, absorbing the movements of the expensive soil and preventing them from affecting the foundation. Then the next is minimizing soil contact. In highly expensive soils, it is essential to minimize the contact between the foundation and the soil. One effective method is to use deep piles or piers that extend into stable strata below the expensive soil. The wall loads are then supported by capping beams that are elevated above the ground level. This design allows the soil to expand and contract without exerting forces on the foundation, thus protecting the structure from any type of damages. Then the next is soil compaction. If the bearing capacity of the soil is low or the soil is very soft, the foundation trench bed should be compacted to improve its stability. This can be done by filling the trench with murum, a type of granular material, and ballast, which are compacted to form a firm base. Compaction reduces the soil's susceptibility to settlement and provides a more stable foundation bed. Then the next is construction timing and plinth protection. Dry period construction. The timing of foundation construction is crucial. Foundations should ideally be constructed during the dry season when the soil's moisture content is low. This reduces the risk of moisture related issues such as swelling and ensures that the foundation is built on the soil's driest, most stable state. Then the next is plinth protection. To prevent water ingress into the soil around the foundation during the rainy season, plinth protection should be provided. This involves creating a slope around the external walls directly water away from the foundation. By preventing water from accumulating near the foundation, the risk of swelling and subsequent foundation movement is minimized. Then the next is suitable foundation types for black cotton soils. Several types of foundations are suitable for use in black cotton soils, each with specific design features to address the challenges posed by expensive soils. First is strip or pad foundations. Strip, pad foundations for walls and pad foundations for columns can be used for structures with medium loads. These foundations should be designed with special considerations such as additional reinforcement or increased depth to counteract the effects of soil movement. Strip foundations are typically continuous, while pad foundations are isolated, both serving to distribute the loads over a broader area to reduce the stress on the soil. Then the next type of foundation is pier foundation with arches. In structures with heavy loads, pier foundations are often used. Piers are deep, isolated columns of concrete that extends or placed at regular interval and extend to a stable, non-expensive soil layer. These piers are then connected by arches made up of concrete or masonry, which distribute the load across the piers. The arches are constructed with a gap above ground level to accommodate soil movement without affecting the structure. This design is particularly effective in mitigating the effects of soil expansion and contraction. Then the next is under rim pile foundations. Under rimmed piles are a specialized type of foundation designed specifically for expensive soils. These piles are shallow with one or more bulbs at their lower ends. These bulbs anchor the foundation below the critical depth of the moisture movement, where the soil is more stable and less prone to swelling and shrinking. The piles are typically 15 centimeter to 50 centimeter in diameter and are spaced at intervals determined by the load requirement of the structure. Then the next is construction process. Under rimmed piles are constructed on site using special under rimming tools that bore the hole for the piles. After the holes are bored, they are filled with concrete and the piles are reinforced to handle both tensile and compressive stresses. The piles are then connected by a rigid capping beam that is elevated above the ground to allow for the soil movements without impacting the superstructure. Then the next topic is footings at different levels. The first topic is stepped footings. Stepped footings are used in situations where the ground level slopes, making it economically unfeasible to provide a level footing base for a structure. This approach involves excavating the foundation trench in a series of steps, allowing the foundation to adapt to the changing ground levels. What are its various design guidelines? First is step heights. The height of each step should not exceed the depth of the concrete block, and each step should preferably be a multiple of thickness of the brick or stone courses used in the construction. This ensures structural stability and uniform load distribution. Then the next is overlap. The overlap between two layers of the foundation concrete should be less than the vertical thickness of the concrete to prevent potential weak points in the foundation. Then what does National Building Code requirements say? According to the National Building Code, the distance from the sloping surface at the base level of the footing to the center of the footing should be at least twice the width of the footing for normal loading conditions. For heavily loaded footing, a slope stability analysis is necessary. The distance from the sloping surface to the lower edge of the footing should be a minimum of 1 meter for soil and 60 centimeter for rock. Dear learners, we have reached the end of today's session. I hope you found it informative and engaging. Thank you for your attention. See you in the next class. Thank you.